Hello, everyone. Thank you for introduction, and I would like to thank the organizers for giving me opportunity and also to give a presentation. So I will talk about some slices of cubic rational functions. Uh, has fixed point, so notation is usually per n lambda. So you have n periodic point, and lambda is the multiplier. Here in our case, we have one periodic, so it has a fixed point, and one means it's parabolic. You can also generalize it for other families, like you have per lambda, per one lambda, and many proofs go through. So here is the content. I give some introduction and setup. And I also talk about accesses to parabolic fixed points. It's a very important notion. And move to the parameter plane. For some, I show some families where it works. And also, so for the proofs, I use Blaschke products, but Blaschke products are, for this case, it's parabolic Blaschke products. So they are not easy to work with. And I give some ideas on the proofs of the main result using some surgeries. So we have one parameter family of rational maps with a persistent parabolic fixed point. So you can send it anywhere you wish. So now you have this multiplier 1. So then you have other fixed points, and you can have little control on them. For instance, you can make them attracting or super attracting. For some other slides, I mean the slice of maps, you can also have another situation. So if you have cubic map, then you can have at most 3 petals. And each petal contains a critical point. I can show you some pictures if you want. So you have parabolic fixed point, and you have immediate basin, and here you have petal P, and you can also have another situation. We have 2 petals, for instance, and here you have some direction, and everybody wants to converge. So here is space of cubic polynomials, which was studied very well in the literature. Here you have, so you have double fixed point. Usually you have like 3 fixed points here. If you exclude the infinity, infinity is also super attracting fixed point. Means you have a control there. And another fixed point here is repelling. I mean, it can be anything. It doesn't need to be repelling. So for rational maps, you have another 2 fixed points. And if you want to have them, so you need a slice, yeah? Then you should control the other fixed points. If you suppose that other fixed points are attracting, you can do a little surgery and make them super attracting. Then immediately your Julia sets will be connected by Shishikura's result. So for cubic case, these are exactly Newton maps of exponential functions. When you compute Newton map, this exponential factor cancels and you get a rational function. In this case, infinity becomes parabolic. And this also works for some parabolic Blaschke products. So in all these cases, you have active critical point, which we call it usually free critical point. So for rational maps, there are 3 such families. So you can have 2 super attracting and 1 parabolic basin. Then you can write it as this one. Of course, you have many, many parameters. We have to kill them by conjugating. And you can send a parabolic fixed point to infinity. You get this one. This comes from Newton map of z squared plus c times e to the power z. Or you can have 1 super attracting and 2 parabolic immediate basins. Then this is a Newton map of z times e to the power z squared, or something like that. Yeah, I think from, yeah, okay. Or you can have a single parabolic fixed point, then you have 3 immediate basins. So each one attracts critical point. So you have one free critical point. And it is a Newton map of only exponential function where you have exponential of some quadratic polynomial. So now parabolic basin, here is a parabolic basin. You have this petal, and if you have points converging to parabolic fixed point, then they must visit this petal and then find this direction and go to the parabolic fixed point. So petal is kind of observing domain. It's open, and on the boundary you have your parabolic fixed point. So it's forward invariant. And you need immediate basin. So immediate basin is one. So you can have, like in for rational situation, you can have another components, and immediate basin is the component of the basin where you have a fixed point on the boundary, or it's a component containing this petal. Now I need to define access to the parabolic fixed point. So imagine you have like for rational case, you have like many components. I think it should be from inside, yeah. And here you can have many ways to go to the parabolic fixed point. So let's take, so you fix some point on the immediate basin. You can also fix like 2 points. And then you take some curve joining them. So there's notation for the gamma Z1, Z0, Z0, Z1. It's any curve. They are on the immediate basin. So let me define what access is. So you have rational function of degree at least 2. And assume you have a parabolic fixed point with multiply 1. And you consider any curve. So you fix some point, and you take any curve converging to the fixed point on the boundary. And now you take its homotopy class, you change this curve, and this homotopy class gives you some access. And this access is called invariant. So if together with its image, but in parabolic domains, you don't have a fixed point. So you always move from point to another point. Then here is your image, fz0. Now so this is your image, say, yeah? Now you have to join it with any curve. That's why I needed that definition. So now you go along this curve and then follow the image of your path. And if you are in the same homotopy class, then it is in the same access. So here is a picture for degree 4 rational map. And for parabolic domains, you have very nice access. So here I can show you. So here is your parabolic fixed point. And as you can see, you have 2 accesses converge to this one. You can go directly, or you can go this way. So you have 2 accesses, but one of them is very important, which is called like dynamical invariant access. So you apply, so you take any curve. Yeah, you start with some point, and then you iterate, and you take, it's all forward images, and you take the union. This gives you 1 access. And this is for various things. This access can be used, and all other access are, so in a sense, this is like attracting or like forward invariant. Everything else is like repelling, or they are invariant under the inverse of your map near the parabolic fixed point. So if you have immediate basin, and it's good to know about these accesses. And here is a first result. So let's take a rational function with connected Julia set. It's important that we have a connected Julia set. For not connected, so many things doesn't work. So you have parabolic fixed point as usual. Now, if you don't have another fixed point on the boundary of the immediate basin, then you can control the number of accesses to this fixed point, and it's exactly the number of critical points. So critical points are very important. And here, every access is also invariant. So if you have like a meromorphic case, you can have accesses which are not invariant. So actually this result prepared last year, but it's actually a very old result. The more generalization was given by on this paper. So this was for meromorphic transcendental maps, where you can have infinite degree. Okay, and also there is a related work on inner functions. Of course, from here we see that critical points are important, and there are many related work by many people on this. Pshititsky also worked on the number of critical points, and Walter Bergweiler also has many results on critical points on the immediate basin, so some bounds. But here we just take the number of critical points and then say some properties of the functions. Okay, here is a cubic family. I think many of you have seen it. So this is per 1 slice. So you see that here it's a butterfly. So when I showed to my daughter, so when I was preparing, and I asked what she sees, and she said it's a butterfly. Yeah, of course it's a butterfly. Yeah. So you have 2 wings. So I will talk about these 2 wings, properties of them, and here is one of those cubic rational maps. So here, and this one, she says, is like human face with big eyes. So parabolic correspond to these gray regions. So you have blue region. So these are parameter planes. So green and blue, looks like blue, yeah. They correspond to super attracting fixed points. So here, fixed points are roots of minus C. There are 2 of them. So on these slides, I mean slices, yeah. So for all kinds of the ones I mentioned here, so you can take all. So you can take the parameters where you have 3 critical point converging to one of those fixed points. Yeah, then you have open components, and they are all connected, and boundaries are Jordan curves. So these are collection of results by many people, and recently, so this guy Zhang, I think, student of Pascal, he generalized it for. I mean, he gave proof in full generality. So here is the main main parabolic component. This is one of the wings. They are symmetric. So these are adjacent type of maps where you have 2 critical points on the same immediate basin. And here is the construction of Peterson and Tanley. So they represented this H0 by Philip Julia set of this polynomial z square plus 1/4. So they just take this petal and then they cut it out and identify the points on the boundary with conjugate. So Z you identify with its conjugate. So 2 vertical points are identified. So, and then you can also get this tessellation, yeah. And this corresponds exactly, this line corresponds to this line then. Here you have points where 2 critical points are on the boundary of this petal. So now Peterson and Tanley showed that this omega, when you identify, carries complex structure. And from here, you can get conformal isomorphism. And recently, Pascal extended it and showed that you can continuously extend it to the boundary, preserving even cusps. Of course, here, cusp is not longer preserved, but every other cusp is preserved. So it is, so this result actually in the previous results, but here it's like my interpretation of the proofs, yeah? So it's not new, but proofs are kind of new, and it's so general that you can apply to many other situations. So you take H0 and it's simply connected, and moreover, two maps, if you have a critical point, if you iterate, they may collide at some point, yeah? So it creates critical orbit relation. If you don't have a relation, then any two map can be globally conjugated together. So in a sense, you can also have parametrization with respect to this quasi-conformal surgery. And if you have this critical orbit relation, it is discrete set. So idea of the proof is soft surgery. So I take parabolic Blaschke products, and I take one of these components, and I do surgery in parallel. And this way, you don't need to track of like in the previous case, you have this fielded Julia set, and you need to parameterize it to give this tessellation, yeah? But here, everything is inside this Blaschke product, which I give you the parameterization. So now you consider some Riemann map. So you have immediate basin. You have a Riemann map, mapping it from the, or sending it to the unit disk. And now if you consider this conjugacy, it gives you a cubic proper map of the unit disk. And that gives you the Blaschke product. Here is the result of Fatou. So the Blaschke product obtained this way has a unique non-repelling fixed point, and that fixed point is parabolic. This multiply 1, and multiplicity 3 means it's a double parabolic fixed point. It means we have two petals around fixed point. And moreover, the Julia set is the whole unit disk. So now this is a Blaschke product, normalized to fix 1. And I take 3 of them for cubic Blaschke products. And you multiply them, you get a Blaschke product. As you can see that to give Blaschke products, you can give its roots, yeah? Or you can give its poles, yeah? So, but we need critical points. So we need to control through critical points. Here is a theorem of Heinz. So if you have any number of points, they're gonna be the critical points of your Blaschke product. Then it says there exists unique Blaschke product of degree d plus 1. With normalization, you can keep the fixed point at 0, and then 1 is fixed. Then this Blaschke product has exactly those points as its critical points. So this is unique. If you have another one, then you can post-compose with another automorphism of the unit disk. So it's very important for us. So now we are interested in cubic Blaschke products. We normalize. And moreover, we want one to be its double parabolic fixed point. So this comes from Fatou lemma. Now this is a model space I consider. So beta 3. So all such Blaschke products. So of course, by Heinz, you can use localization of, so you can have a fixed point, one of the fixed points. But if you have two fixed points, you can send it to either 0, one of them, and another one gives you parameterization, yeah? So, but of course you have a choice, yeah? So now for cubic, you have 3 complex parameters, and you want to get rid of as many parameters as possible and obtain some normal form, yeah? And here you can exclude two parameters and obtain only the family depending on only one parameter. So this is how you can do it. You can just take the, you take the, so let's see. Yeah, you can look at the image of the critical point as 0, and you can post-compose with some Blaschke product, sending it back to 0. Yeah, then you must have origin as a fixed point, and you can uniquely factor it like this. So this way, this is a nice normal form, yeah. But this normal form is bad for iteration, but you cannot do better. So if you have a double, then you have this explicit expression. So in other cases, yes, it gets very complicated because of this I mean, it's not holomorphic. Yeah, you see, only real analytically, you can find a relation. So this is for the critical point if you have B. Now you have this U, yeah, you have to get rid of. So here is the approximation. Now to get rid of this U, you need to require that one is your parabolic. You never used it. So now if you require that it's a parabolic fixed point, then you can find this another parameter. Yeah, again, so for given B, you know your critical point. So B is from the unit disk. You know your parameter A, and you have this normal form. And also this normal form gives you the case when you have double critical point at the origin. And also it gives you this explicit example. Okay, as we can see, it depends real analytically, and critical point also depends real analytically and bijectively on the parameter plane. I mean on the parameter B. Now you have two critical points. You can also send them to symmetric points, yeah, C and minus C. Yeah, then you can also find this C explicitly in terms of the critical point. So this is old critical point. Old critical point is related to this parameter B. So this way, you can get even longer formula. And now you can also do this. So as I told you, you cannot do beta. Yeah. Now, but here you have symmetrical, so you can see the moduli space immediately. Okay, let me state it as some proposition. Also in this case, we have this one. Now, since you have choice, so it creates you some moduli space, yeah? So now I was able to find the group action here. So the conjugacy classes is like has orbifold structure, and so origin is the elliptic point of order 2, and I was able to find explicitly this group action. So if you have critical points related to this, then they are on the same conformal class. Yeah. Now, how about this another representation? Well, then it is group action is given by z square, or you can say it C goes to minus C. And also you can find the conjugacy of these group actions. So it's exactly this critical point, yeah? So now critical orbit relations. So this is definition of a critical orbit relation. Some orbits, some iterates of one lands to the another iterates of another critical point. So here we consider only the case when critical points are not the same. So this is, and I iterate two critical points. So now little I say a little bit about how to find them or how to generate them. So you can, of course, start by our parameterization, or you can do better by considering all the space of cubic maps. So you can consider the Brandner-Haber form. It has this, and here what's nice is your critical points are at plus minus a now. Before, critical points solve quadratic equation, and marking is super hard for that case. Here they are marked at plus minus a. So you can identify the space, these two parameters, a or b, but some of them are conjugate, and the moduli space gives you by coordinates a square and b square. So here is another result. So how to represent this slice? So you just take this, so discriminant of this polynomial in Brandner-Haber form minus z. So you are solving fixed point equation, and you ask to have two fixed, double fixed point, yeah? That gives you exactly solution, common solution of your map and its derivative, yeah? Polynomial minus identity and its derivative. So this gives you discriminant. That's why from the, if you remember, there is a 4 and there is a 27, yeah? So this represents per 1, and all cubic maps of this can be obtained by some level sets of some polynomials explicitly. And all critical relations are realized except 1 and 1. For 1 case, you should have degree at least 4, because when you map two critical points, if they land, each one needs 2 pre-images nearby. So you have 4 pre-images. So you should have degree 4. That's why here it's never realized 1 and 1, but all others are realized. And here are explicit formulas for the polynomials. So you can iteratively find these intermediate polynomials recursively, and relating them, you can explicitly find the level sets of polynomials. And here is an open problem. So prove that these polynomials are all irreducible. It seems that it's super hard. I did a lot of experiments and was able to show it only for very, very simple case. Because this Eisenstein, you have to play with Eisenstein criterion, and you have to fix some value for one parameter, and it's one variable polynomial, and you have to play with some moduli. You should go to mod Z. The Z mod P, and you have to see all kinds of prime numbers. And here, in one case, it worked for mod 17. So it means I checked it for all prime numbers smaller than 17, yeah? And okay, so here is an example of a Blaschke product now. You can use this normal form, and you can, so you have two cases, yeah? 0 can map to W, or W can map to 0, yeah? Here, if you consider W mapping to 0, then you can use some symbolic software like Mathematica or others, and you can find a parameter. But doing it with hand is hard because of the formula, you remember? It's very long, and there is a root, yeah? And you can also do another approach here. You can use another representation. And now you can use Gauss-Lucas theorem for Blaschke products, yeah? But just for this case. Gauss-Lucas says, so critical points belong to the hyperbolic convex hull of the zeros. Since your 0 is at 0, so hyperbolic line in your case is also a Euclidean line. So using this fact, you can find explicitly these parameters. Of course, by hand, this is really hard. Now I give the proof idea of the result about the H0, so it's wings of the butterfly. So now you take, I think I have time, yeah? Oh, yeah. So you take, so there is a center, which is when you have critical point. So you have two critical points colliding, yeah? And you take that one, and then you perturb it little bit. And what happens is that now you have two critical points, and they are so close each other that if you iterate one of them once, you are inside of your petal. So let me show you here. So let's say you have critical point and you have a petal. So if you perturb it little bit, now it lands inside, yeah, very little bit. So now, what is this? So here I'm doing quasiconformal surgery. I started with the parameter where you have two critical point colliding. So then, yeah, this is first case. Another case is when you perturb it, then two critical points are then on the boundary of this maximal petal, yeah? So this maximal petal is the one, when you have Fatou coordinate, it sends you to the right half plane. You can normalize. So here is the surgery I do. So for the second case, or the first case in our situation, in one iterate, it lands to the parabolic, to the petal. Then on the Fatou coordinates, you have this right half plane, and this is the position of the image of the critical point. Now, you can consider quasi-conformal map sending these ones to the straight lines. These are linear maps. You can immediately find the formulas for them. And this gives you soft surgery. So it flattens those curves to straight line. And from here, you see that this critical point now has this position. Of course, you can send it to any other points on this strip. So here is another situation. So this second case. So you, of course, here origin is another critical point, and this is kind of your free critical point. Now you can send it to any point on this boundary, yeah? So it's here in this case, its y coordinate goes to 2y. You can also do it for any multiples of y, so k times second coordinate. So these are all quasi-conformal maps. And here is another situation. So this is called, so on the Fatou coordinate, if you quotient out by dynamics, you have bi-infinite cylinder, and you have a position of a critical point, and you can twist it and change its position. And here is the picture of twist. So I take little square, and I move it to the right, or you can also move it to the left, and you can move it to with any length, yeah? You can make it longer and longer, and then you propagate this by dynamics. You should also have these lines, yeah? And these are also quasi-conformal maps. Okay, so you have maximal petal is one critical point, and you have Fatou coordinate. Of course, you normalize it, and you have another critical point, which is on the boundary or on the inside when you iterate. Now you take on the Fatou coordinate some so image. Let's call it W0. Now I show you some formulas for the quasi-conformal homeomorphism of this strip. So now here, from any point, you can go to another point. So you fix 2 points. You consider this difference. So H and T. So by playing with H and T, you can reach to any other point. And here is the quasiconformal map. And you extend it by the on the right strips by sending z goes to z plus 1. And you can also compute the real dilatation. So these are quasi-conformal. This way you can do global homeomorph, globally conjugacy on the maps with critical points. So here, if you started with, you can get all kinds of maps where, so in other words, here is your critical point and it lands, you can reach to anywhere. Of course, these are the orbits of your first critical point. Yeah, you cannot hit them, but you can hit any other position. Okay, so now you pull it back by Fatou coordinate and put almost complex structure on the petal. And of course, if you have another components, you pull it back by the dynamics of your map, and everywhere else you put standard complex structure. So this is FA invariant. And by using measurable mapping theorem, you find quasi-conformal map on the whole complex plane with the same Beltrami equation. So you normalize it, then this composition is again, in our case, it's a polynomial. If you take another slice, it will be on the same space because you are not changing on the rest of this basin. So you are doing it only locally. So this is again the same on the same space. So now you look to the coordinate of the another fixed point, I mean another critical point. Then since you shifted by H on the horizontal and T on the vertical, you get any map that you started. So this is now coordinate of this obtained map on the Fatou coordinate. So this way, very easy construction. You can have like the whole strips, yeah. So these are the tessellations of the parameter plane. Of course, here you have more structure. So the tessellations come from the right half plane, but you can also cut them along these strips. So now, for the other cases, you have, after some iterates, they reach, yeah? Then, of course, you perturb it very little bit. And again, for instance, you are in a situation that it maps, so another critical point does it has orbit, and then it reaches to the orbit of the first critical point. Maybe it reached here, yeah? Yeah, it did like, how many I have here? N. So here, N times you iterate. So this is 0, yeah? 0 is on the Fatou coordinates, your first critical point. So it's N times. Now here, you did M minus 1 times in the immediate basin, and then it reaches here in the last iterate. So now they are Fm times C2. Now, again, the same construction works. You perturb it very little. You have two situations. Of course, here you can have three situations. You are either here, or you are on this image of the boundary of the petal, or you are here. So you can have like three situations. Of course, with the same construction, you can change it by the surgery. And you can also bring it to anywhere you wish by twisting. You can move the coordinates backwards and forward. Also go there. So this way, you are again conjugating them globally. So this is the idea of the proof. Now to finish the proof, what you do is, as you can see that it doesn't matter where you are doing this surgery. Now you take as a model map the Blaschke family. You know that it's parameterized by complex number B, and its moduli space is simply connected. So you do it parallel. So for Blaschke on one side, and on your slides, on your slices on another. So you do it in parallel. You change for Blaschke, and you change these coordinates for your maps. And you send the maps for Blaschke to the maps on the Fatou coordinate to your slice. So this defines you, since everything moves holomorphically and continuously, this gives you homeomorphism from the moduli space of parabolic maps to this H0 component of this slide. I mean slice, yeah? So, or you can do it like this. So, do I have another slide? So, for the Beltrami equation, you have continuous dependence on parameters, yeah? So here you continuously change, and here you continuously change. So this gives you like correspondence or the map, yeah? So this way, you kind of don't worry about this tessellation structure, because here you can have, okay, n times I reached here, m times I reached there. Don't worry about it. If you read all other results, it's very complicated because you need to keep track of everything, yeah? You can also use the boundary behavior, but here, automatically you obtain the simply connectedness by the moduli space of Blaschke products. So for this to work, you need connected Julia set, and you should have two critical points in the basin. And everything works automatically. Do I have time or? I think I finished. Yeah, thank you.
Questions or perhaps any comments? I have one question. At the beginning of the talk, you were having this path inside of the basin of a parabolic basin, and then counting the number of distinct paths that you can reach the point. But there were one assumption that it was no other fixed point on the boundary.
Yeah, this is it.
Yeah, but then in the case that there are other fixed points in the boundary, meaning it is an open thing, or it is everything can happen.
For polynomials, it doesn't work because for most of the time you have another fixed point on the boundary. Then in this situation, you have a Jordan curve automatically. You have only one access. But for rational maps, so the proof idea was you have to find this Blaschke product. And for the Blaschke, parabolic Blaschke product, you have, so one is a attracting parabolic fixed point, and all other fixed points are repelling. And the idea was from each this repelling fixed point gives you one access. So if you have another fixed point, then this idea doesn't work. Yeah. So you need connected Julia set and no other fixed point. So it can, yeah. Also, Blaschke also it doesn't work because automatically you have another fixed points. So I excluded Blaschke case and the case of another fixed point, then everything works. Actually, the result that published previous year It was very old, so I submitted it like 2017 or 18, but then took a year to review it, yeah. And then review came positive, but they say there is little gap. But I adapted it for the super attracting case. So it means there is a gap in the other works. But the review was so nice and gave proof ideas, but it took some time. Meanwhile, I had like teaching position. There was no need to publish it. So then I found time and submitted, and then they considered it as a new submission, and yeah.
Question, but with the access to the parabolic fixed point, isn't an immediate parabolic basin usually simply connected?
Not necessarily.
Yeah, not necessarily. You can have like disconnected, Julia said. Yeah, you can have another inside. Yeah, it doesn't need to be. For connected, yes, it is simply connected, Julia said.
Basin.
Yeah, it doesn't need to be.
Yeah, that's why it's very important in our cases that they have connected, Julia said. So, and then you have immediate parabolic basin as a simply connected, so you have a Riemann map. And you send it to the open unit disk by the Riemann map, and then you work with Blaschke product. Otherwise, you have degenerate Blaschke product, disconnect, like, I mean, the Julia set is not the unit disk, and many things can happen there.
Any more questions? No, let's thank the speaker.